Hi, everyone. Thank you for attending today's webcast, Thinking of Hot Water as a System. I'm Kanchan Swaroop. I'm with the Appliance Standards Awareness Project, and I'll be moderating this session. I just want to start off with a few housekeeping announcements, and then we'll quickly move on to our speakers, followed by a Q&A. So first, as a reminder, your screen is customizable, utilizing the various widgets found at the bottom of your screen. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode, but can submit questions through the Q&A box at any time during the webcast, and presenters will be answering questions following all the presentations. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. Zoom discussion rooms will open at the end of the webcast to continue conversations and allow for additional questions. Click on the Zoom widget or download the daily Zoom link PDF available on the Engagement Hub. Last, we want to thank our sponsors and partners for their support of the Hot Water Forum. And now I would like to introduce our panel of speakers. Our first speaker is Bob Staton from Sage Hill Enterprises. Then will be Troy Sherman from Evolve Technologies and Brian Hageman from Mazzetti. We'll start with our first speaker, Bob Staton. Bob taught solar energy for a decade at Cabrillo College and is the author of 2 books on solar energy. He lived in an off-grid solar home for 20 years, and Bob will discuss a new method of passive freeze protection for flat plate Thermosyphon solar thermal water heaters. Bob, take it away.
All right. Can you hear me all right?
Yes.
Okay. Well, thank you for the opportunity to present my idea today. Let me be clear about expectations here. What I'm giving you is a design principle for freeze protection system for solar Thermosyphon systems. It's not a product, it's not a patent, it's an idea that also with a working example. But I believe this is an idea worth spreading, as they say in TED Talks. Thermosyphon systems are remarkably simple. If you look at the diagram here, you can see it's just a basic loop with a solar collector and a storage tank, and the basic design principle for that is you mount a tank above a flat plate solar collector. You plumb the top of the collector to the top of the tank, and you plumb the bottom of the collector to the bottom of the tank. It's simplicity itself. Thermosyphon systems operate when the sun shines on the collector and warms it up, and the warm water, rises into the elevated tank, and the coldest water at the bottom of the tank sinks down into the bottom of the collector, creating a circulation loop. The advantages of Thermosyphon are many. They are completely automatic. They flow when the collector is warmer than the tank, and they stop when it's not. There are no complicated parts to fail. There's no heat exchanger or toxic fluids. No electricity is required. It's inexpensive, and it's simple enough to do yourself. Thermosyphon has a couple of disadvantages. One is that in the design, the tank must be above the collector in order for the warm water to rise into it. If you have a source of water and an open system, that is, the system is operating at the house pressure as part of the pressurized system, then you could have a problem with hard water creating scale inside the collector because you're circulating water, ordinary water, through the collector. And because it's a Thermosyphon system, it has relatively slow circulation compared to a pump system. So there would be more heat loss, and it would be a little bit less efficient than a pump system. But of course, the big disadvantage with the Thermosyphon system is its Achilles heel, which is freezing. It's an unfortunate property of water that it expands when it freezes, and the pressure on it can burst the pipes in the solar water heating collector. And a single cold night is enough to ruin your collector. So people have put in place various freeze protection solutions in order to prevent solar water heating systems from experiencing those broken pipes. A drain down system, a drain back system, antifreeze with a heat exchanger, But any of these create complications, so it's no longer simple and no longer cheap. So I went back to basics, and when I was teaching at Cabrillo College and explaining thermosyphon systems, I would clarify for my students that the basic idea that they have that warm water rises is actually not quite correct, because when you add heat to water, it doesn't acquire anti-gravity properties and cause it to go up. In actual fact, what happens is the warm water expands, becomes less dense, and the cold water, which hasn't expanded, is more dense. And so it's the cold water sinking that drives a thermosyphon system. And in a loop, when the cold water sinks, that lifts the warm water, creating the circulation loop that makes the thermosyphon work. But the basic principle is that cold water sinks because it is more dense. So my new solution works on that principle, which is to allow the cold water in the collector to sink. And you do that by adding a second loop to the thermosyphon system. You have the normal loop where the solar collector feeds water up to the storage tank, but you have a second loop with a heat source below the collector. In heating mode, the coldest water in the storage tank sinks into the solar collector, driving the warmer water up into the storage tank. So this is the normal thermosyphon heating mode. But when it's cold and the water in the collector is cold enough to sink, then it sinks down into a heat source, which then warms the water and then is carried back up into the collector. So by sinking into some sort of a heat source, it prevents the water in the collector from freezing, and the circulation brings the warm water back up to the collector and keeps the collector temperature high enough so that the water in it doesn't freeze. So if you want to put a heat source below a collector, the engineer might think that, well, the first thing you do is you create an active heater with a thermostat, and the thermostat turns on when the water gets cold. But you actually don't need that because the heating requirements here are pretty minimal. What you need to do is keep the temperature above 4 degrees C, which is the highest density point of water. And that's relatively easy to do. You can do it with ambient heating from a building, or you can do it with ground heat from a buried coil. So I want to be clear that this is not just a theory. This is my example of a solar water heating system that incorporates this. I acquired these solar panels secondhand, actually for free, because someone was removing them from their roof. They're copper plate collectors with copper pipes, very nice, a little bit aged, but they work just fine. I set them up with a normal thermosyphon system. In my case, they were on a hillside below the house. So I buried the pipes in the ground with a great deal of insulation and protection. And they rise about 17 vertical feet into a tank that's in the house. And that's the basic heating loop for the thermosyphon. And of course, I wanted to prevent this from freezing. So I added the lower freeze protection loop, which is a second loop of copper pipe plumbed into the same connections, but going down instead of up. And at the end of those circulation pipes, I buried a coil of copper pipe. I was fortunate enough to find 1-inch coiled copper to do this, so that I could run a long length of pipe without very many joints and be able to easily form it into a coil. And I buried this about 3 feet deep in the ground. And it works. I put this in service in September of 1999. I'm located in Northern California, and we experience a few freezing nights per year. We get in as low as the low 20s. And there'd be frost on the ground, but not on my collectors. And I had no burst pipes. And this system operates with literally zero maintenance. It just continues to operate and has operated for 20 years, providing me with hot water without freezing. So if you want to incorporate this design principle, there's several things you need to consider. First of all is the climate. I don't think I would try and do this in North Dakota. because the heating requirements to keep the collector from freezing in the winter of North Dakota would probably be more than the heat you would get from the solar water heater, and wouldn't be worth it unless you wanted to drain the system during the winter months and operate it only in 3 seasons, which would be fine. The height difference matters. The greater the height difference, the higher the heat flow, but then, of course, you have longer pipe runs. The pipe diameter is significant. I tried to go with a 1-inch pipe so that to reduce the friction in the pipe. And you want to minimize the number of pipe joints and bends in the pipe because thermosyphon flow is rather gentle, and you don't want to create too many blocks to inhibit the flow. You want to insulate the pipes thoroughly. You don't want to lose heat, and you don't want to expose pipes to the freezing temperatures. You have to consider the rate of heat flow from your heat source that's below the collector. Sometimes that's hard to judge, and in my case, it was pretty much I just made the biggest coil I could and put it in the ground. And you also have to consider the reliability of the heat source. So if it is an active system, then you have to worry about power outages and it not working. But in my case, burying a coil in the ground, well, that's a very reliable source of heat. The home example I give you is from 1913, showing a picture from the book by Ken Booty and John Perlin of a solar water heating system installed in Southern California with a flat plate collector circulating water up into the tank stored in the attic. And the reason I mentioned 1913, because that was the year that they had a hard freeze in Southern California, and many of these systems that were in place at the time froze, and the pipes burst, and the company was running around trying to fix everyone and keep their customers happy. If, at the time, they had installed a second loop to carry the coldest water from the collector down into a heat exchanger down in the basement, for example, with a return line to bring the warm water back up to the collector, then they could have prevented those freezes. And, of course, this technology was available at the time because it's the same principle that the heating system operates on. So it would have possibly changed the course of solar water heating in Southern California if they had had this design principle. The potential for this is on several different areas. Of course, do it yourself, as I have demonstrated, because it is so simple. It's just plumbing. And that also means it's inexpensive, so it could be done in developing countries. Remote locations are particularly advantageous because it doesn't require electricity. And, of course, this could be incorporated into commercial products. There's a lot of thermosyphon water heating systems all over Europe. When I toured in Greece and Italy, I saw many of these on rooftops. Most of these are set up with a heat exchanger and a heat transfer fluid to prevent from freezing. But they could make them less expensive as an open system if they run a second set of pipes down into the living structure, which is, of course, generally below the collector if it's mounted on the roof. So these are just some of the ideas. I'm putting this idea out there because I think it has a lot of potential for application around the world. If you think in terms of where thermosyphon systems can operate today, normally you wouldn't want to put it in any place where you would have any freezing at all. So that limits the range to pretty much the tropics. But this idea, adding it on, expands the range of thermosyphon water heating systems into northern, southern latitudes that would normally not be suitable for it. So I think it has a lot of potential, and I'd like to see it get out there. So that's why I made this idea available in this forum. So thank you very much. Over to you.
Thanks, Bob. Our next speaker is Troy Sherman. Troy is the co-founder of Evolve Technologies. He spent the past 15 years immersed in the issue of shower warm-up waste and reducing or eliminating it without requiring behavior change. Evolve Technologies products are currently used as measures in the largest energy efficiency and weatherization programs throughout the U.S. Troy will take a look at the interaction of water-sent shower heads and the time it takes to clear out the structural waste at the start of a shower event. Go ahead, Troy.
Alrighty. Thank you, Kanchan. Appreciate it. Yeah, so today we're going to talk a little bit about shower heads and water-sent shower heads in particular. And as many of you know, water-sent shower heads are great. They save water, they save energy, they are designed to have good pressure sprays, good coverage and warmth. And the penetration in the market is actually really high now. It's about 45.5%, closer to 50%, with around 141 million installed. But there are some challenges that WaterSense shower heads do create. The truth is they're accidentally causing significant water and energy waste when we warm up our showers. If you take a look, obviously lowering flow rate is going to increase wait times, and WaterSense shower heads make wait times worse. If you just did linear math, you would anticipate that we've had about a 2x increase in wait time since the 1990s, just putting on lower flow shower heads. In the 80s, for example, at 3.5 gallons per minute flow rate, you would expect water to arrive in about 26 seconds. In the 90s, it would have bumped up into 36 seconds at around 2.5 gallons. Today, at around 1.5 gallon flow rates, you would be expecting around a minute to wait for your hot water to arrive. And tomorrow, shower heads are starting to go even lower at flow rates of like 1.25 gallons per minute. You're talking around 72 seconds. Again, this is just a linear calculation, but what we're going to learn here is that's not the right calculation for hot water waits because there's thermal losses along the way. So what happens is WaterSense are creating flows that are even lower than we'd ever think. And it's due to a combination of flow regulators, pressure, and mixing valves. So the flow regulators that would go into a WaterSense shower head basically come in like a 1.75, a 1.5, a 1.25, but they don't actually flow at those rates. The manufacturers designed them to have a little headroom in them, so they actually flow a little bit less. So when you're doing your WaterSense testing, you don't bump up above the flow rate and not pass the testing. The other thing that influences how much water flows through or the flow rate is the pressure in the home. At a typical home, say you may have pressure in around the 45 to 50. WaterSense will let you flow at lower flow rates, and even pressure compensating regulators will do this. So what you think is a 1.75 or is labeled as a 1.75 shower head may be flowing at only 1.31. You get down to 1.25 and you can see that it's flowing less than a gallon per minute. And then we have the introduction of mixing valves. Mixing valves, even when you're full hot, are mixing hot and cold together. And so a typical mix ratio may be like an 85 to 15 mix. At the end of the day, what I'm trying to show you is that flow rates actually start to get pretty low on the hot water line, even when you're using a 1.8, 1.75 GPM shower head that's WaterSense, you're likely only flowing around a gallon a minute on the hot water line itself. And that starts to have a really big impact on the amount of water that we actually have to purge. And this is where we start to get into a curve equation rather than just that linear equation that I was talking about before. Back before 1992, when EPAC was introduced, water flowed out of a shower head as fast as it could flow. You might have it be at plug flow, which basically is really good delineation between the hot and cold. And I don't really have very many thermal losses, so I'm not creating more water to purge when I'm flowing at a really high flow rate. 1992, the EPAC legislation came in, and you're starting to see on the hot water line what we would call long bullet flows in the shower. The water traveling to the shower, where I can actually be increasing the volume that I have to purge by 10 to 50% because there's thermal losses due to radiation to the pipe itself, as well as intermixing of the hot and cold as the hot travels through the shower head. We get into WaterSense, and as I demonstrated, we can get flow rates on the hot water line that are under a gallon a minute, which can actually increase the total volume that you have to purge due to thermal losses by 50 to 100%. So what we are actually seeing today is that our wait times aren't increasing 2x, they're actually increasing up to 6x when you have a WaterSense shower head. So for example, what used to be a 15 to 30 second wait could very now easily be 2 to 3 minutes. And waiting for hot water is inconvenient, so people have developed a habit of doing other things while they're waiting. Most of us, about 3/4 of us, do other activities while we wait for our hot water to arrive at the shower. And a lot of us, about half of us, are stringing together a bunch of activities. So we may brush our teeth, we may use the toilet, grab a towel, and then return to the shower. And we're returning to the shower after we're done with our activities, not when the hot water actually arrives. And so what happens today is about 30% of a shower is wasted before showering ever begins. You've got about 2 minutes of an empty shower running, And then you've got about 6 minutes of showering for your total time of 8 minutes of a shower event. Let's take a look at the problem. Essentially, we put sensors on shower heads to gauge basically time and temp and to get an understanding of how people are using their shower. And so you turn your shower on and you may be getting a temperature reading of around 70. You'll see the temperature start to drop because you'll have some water that's coming in from outside basically the insulation envelope. And then you'll start to see a profile where you have the water warming and reaching a maximum plateau. That max plateau is basically the highest temperature the shower can reach based on where you have your mixing valve set. Then we'll see a drop to what I would call a bathing temperature plateau. And that bathing temp is really easy to identify because people shower in a very narrow band of around 100 to 105 degrees. And so this is a little exaggerated, but this is what a typical curve looks like when you look at how somebody is using their shower. What we see when we look at this problem is about 40% of the waste that happens is cold water that we have to purge before the hot water can arrive. But around 60% of it, the majority of it, is behavioral waste. That's hot water going down the drain. So hot water's arrived, but somebody's away from the shower doing something else. So let's take a look at how long we should have to wait for hot water. Well, according to the American Society of Plumbing Engineers, the ideal is less than a 10-second wait, but not more than 30 seconds. And we've already seen that we're waiting much, much longer with that when we're talking about water-sense shower heads. So what if we could shift the problem? What if there was a way to get rid of your structural waste very fast? If we could do that in a curve like this, you'd start to see structural arrive super fast. Say you're purging your water in about 15, 18 seconds. And then you have what would be called this behavioral portion. But we can save the behavioral portion by shutting off the flow of water once hot water arrives with a little thermostat inside a valve that's connected to a shower head. So we can save the overwhelming majority of water that's getting wasted today while we're waiting for our showers to get warm. And we can do this through a technology that's called Shower Start Express. Basically, it allows for faster hot water, warm-up freedom, and it allows you to save hot water. And basically how it works is you turn on your shower, and there's a port where you see this arrow pointing down towards the back of the shower head that lets the cold water purge at around 4 to 5 gallons per minute. Once the hot water has arrived, the port, the express port we call it, starts to trickle. And basically it's preventing your hot water from running down the drain while the user, the bather, is still away from the shower. When they're ready to shower, they just press a tab or they pull a cord. The shower flows as it normally would. And the system then resets itself for the next use. So one of the big advantages of this, again, is from a convenience standpoint, I get faster hot water. And as we just discussed before, the increasing the velocity of the water actually reduces how much hot water that you have to meet when you're getting your shower warm, because you're not losing any of that hot water to thermal losses. So with a shower head with a Shower Start Express at a 4 to 5 gallon purge rate, you'd be getting your hot water in about 18 seconds. In comparison, if you had a 1.75 GPM shower head, if you did your basic math, you'd be looking at around 51 seconds, almost a minute for the water to arrive. But in reality, it could be as long as about 2 minutes for it to arrive. And then you get down to 1.5 gallon shower heads, you'd be looking at 60 seconds for the hot water to arrive in a linear calculation. But as we've shown with the thermal losses, that could be as much as around 3 minutes for hot water to arrive. The other big advantage is that you get warm-up freedom with this technology. Basically, the cold purge as it arrives, and then there's no more empty shower running on and on while somebody's away doing their general activities. We also get, and this is really important, we get an opportunity to save hot water. As we mentioned before, you get faster hot water, which your shower gets to warm up around 6x faster. You also get to enjoy more, right? My hot water arrives in seconds, and there's no more waiting, standing by, waiting for hot water to arrive. The other advantage that you get in saving hot water is you get your warm-up freedom. You get the shower head that auto-pauses once the hot water arrives. It gives you the opportunity to multitask while you're waiting for hot water. There's no more empty showers running on, and you also know when your hot water has arrived. And this saves a bunch of water. you get to use up to 50% less getting your shower warm for the hot water to actually arrive at the shower, and the total volume of warm-up waste that's hot water going down the drain can be reduced by about 85%. There's also an option on this technology to add a hose and collect the structural waste or that cold water that needs to get purged. When you're warming up your shower, you could save the 1.5 to 2 gallons that you're purging in a receptacle and then use that for later use. I guess thank you. I guess we're going to do questions later. And Kanchan, I'll turn it back over to you.
Thanks, Troy. Yeah, if anybody has any questions, please just enter them in the chat and we'll answer them at the end of all the presentations. Now we're going to hear from Brian Hagman. Brian is a plumbing engineer with Mazzetti, designing and managing the integration of MEP systems to support healthcare organizations for over 30 years. Brian will explore the implications of using one-pipe systems to bring water to hand washing sinks on occupant health and safety, including Legionella risk. Go ahead, Brian.
Thank you so much for the opportunity. Great presentations, Bob and Troy. What I want to talk about was considering the elimination of hot water from hand washing, and my focus has been in healthcare for the last 30 years. And I've seen a lot of what Troy was talking about, issues with the pipes cooling off and then wait times for hot water. And what we've been seeing is that in general, the systems have gotten lower and lower flows, and dead leg pipes to hand wash fixtures have cooled, and people are generally completing their hand washing with water that has basically reached the ambient temperature of the building. And so the topics today are going to be, we don't need hot water for hand washing. We may not want hot water for hand washing, some current design approaches and how codes and goals and costs drive the current design approaches and some of the problems that spring from that. And then some ideas for designing for better use of water and energy, and some sample design concepts. We may get to codes, I'm not sure. So first I want to make sure that we're clear about what I'm talking about here specifically is hand washing. And when I think about healthcare, for instance, hand washing is so different from bathing, where bathing, you need full immersion. And it's very infrequent that patients bathe in actual hospital settings. The danger in bathing is scalding because of the full immersion. And hand washing is just hand immersion, and it's very frequent, especially for staff. They are mandated to wash their hands very frequently throughout the day. So their exposure to the contents of that water is much increased more than bathing happens in healthcare. The danger of scalding is much lower due to the mobility, your ability to remove your hands. So we don't need hot water. It's been shown by many, many, many studies that water temperature within the range that we can comfortably, safely wash our hands, that the temperature range does not have any impact on bacterial removal. They found no evidence in multiple studies that there's any difference between bacterial removal efficacy for water that's 40 degrees versus water that's 120 degrees. So that starts to make me think it's not necessary from a health standpoint to use that hot water. It's purely comfort. And you actually may not want hot water if you're having to wash your hands throughout the day very frequently. They've actually found that there is a there's a dermatological impact from frequent washing of hands in hot water. Multiple studies, again, have shown that the use of very hot water for hand washing should be avoided as it increases the likelihood of skin damage. Even healthcare infection control practices guidance committee says avoid using hot water for hand washing because that repeated exposure to hot water may increase the risk of dermatitis. And what follows after dermatitis is actually a roughening of the skin, which results in even more harboring of bacteria and more difficulty in freeing your hands of that bacteria. So we don't necessarily need hot water. We don't necessarily want hot water, but we are putting a tremendous amount of cost and energy into providing these hot water systems. And along with that, one of the things that we're trying to ameliorate to a larger extent these days than we used to is the results of waterborne pathogens. And we'll see how that temperature of the water and age of the water in water systems exacerbates this problem. So it's in a typical system, you've got this is specifically, again, more geared for something like a clinic or a healthcare facility, recirculated hot water piping that hopefully is somewhere above 120 degrees circulating, but where it goes to every fixture, there is a dead leg of hot water pipe, and there's a cold water pipe. And then there's also a mixing valve. In a lot of cases, there is a sensor faucet. These fixtures are frequently used because they're mandated to be used in most cases. However, for instance, in patient rooms, we've been finding that unless there's a C. diff patient or something like that, that's very specifically, doctors, nurses tend to gel in, gel out. And they consider those staff hand wash fixtures within the patient room to be kind of a nasty, dirty thing. So some fixtures are frequently used, others are not, and the flows are very low. So that temperature in the dead leg of hot water pipe can be very, very unpredictable, and it may well get into the temperature range where waterborne pathogens such as Legionella can grow very well. We have cold water that is basically cooled to the temperature of the ambient temperature of the building. And since the faucets are low flow and they flow half water, half cold and half hot, those cold water systems experience water age issues too. But there are very, very, very few documented cases of Legionella or waterborne pathogen issues coming from the cold water systems. So if we're looking for the factors that we would want to incorporate in designing for better use of water and energy, we would want an antibacterial system with no water between 68 and 122 to stay out of that temperature range, no stagnant water, and a simple system with nooks and crannies. Why is that so difficult to get? Well, keeping out of this temperature range, code requires hot water from fixtures to be between 105 and 120 Fahrenheit. In California, OSHPD requires high temperature alarm, which leads to master mixing valves and originating delivery temperature starting at 120 and loss of temperature from there. No stagnant water is really difficult to achieve because of low flows dictated by code, and low flows desired by lead, and high cost. Why is it impossible to get a simple system oftentimes is because either the code or the facility has a required redundancy of the domestic hot water supply equipment, and they also code mandate sensor faucets, which then require mixing valves, and we start to add more and more components at every fixture, which expands the real estate that's available for waterborne pathogens to take hold. So if we start to think about how to design for a better use of water and energy, we eliminate this much of this piping system that is basically the hot water and cold water two-pipe system. The hot water system is consistently losing energy through its insulation, and those systems tend to be spread throughout the entire floor plate of a healthcare facility or a clinic. So you're basically creating a giant energy leak throughout the building. If we were to remove the hot water system from the fixtures that don't need hot water, unlike the bathing fixtures where we do want hot water, we eliminate a large quantity of the piping system, and that we still have that water that's reached the ambient temperature of the building, which is just as effective for hand washing as hot water. What we get if we pull out that two-pipe system from hand washing fixtures is we reduce the water heater size, we reduce the energy used to heat and maintain water temp. We have found that, let's say we have a clinic that has 60,000 square feet, that would be about 100 fixtures spread throughout the floor plate. And since we have that temperature issue with wanting to keep our water hot so it's safely out of the waterborne pathogen growth growth range, we have to circulate all the time. And we find that you spend more energy circulating, heating that recirculated water to replace the water that's been lost through the insulation than you do spend on heating water that's actually been used to wash hands. You reduce the amount of piping, valves, mixing valves, hangers, everything. And you reduce installation costs and maintenance costs. And to me, almost more importantly, is you reduce the overall volume of water that's sitting in pipes. Because you have a two-pipe system, when you reduce that to a single-pipe system for hand washing and you remove so much of that water, you remove water that's been sitting and waiting to be used. So there's less water age, and the removal of so many feet of pipe also results in less overall biofilm real estate. You reduce infection control issues at faucets, and you reduce the dermatological impact of frequent hand washing. A quick design example I took that we had in our office was a 60,000 square foot office building, runs 8 hours a day, but they do have to recirculate all the time to keep it out of the growth range. A facility of that size that have about 100 hand wash fixtures, and then very, very few fixtures that really do require hot water. A way to approach it would be to provide a central water heater with 140-degree storage to provide hot water to those fixtures that do need hot water. And then a single temp system. Here in California, we probably wouldn't even need to heat the water from the cold water incoming to get it to 75 degrees, let's say. If you have colder incoming water, you can use that central heater with a mixing valve to get it up closer to the range of the building's ambient temperature. And then you would run cold water to flushing fixtures. If you had to heat that water, it'd be better to use just the cold water incoming. On that sample project, you had a 25% overall reduction in piping, which could have been much, much greater if we kind of co-located the hot water use fixtures. We would have a 60% reduction in insulation for hot water piping, 25% reduction in water heater capacity, 36% energy reduction in hot water heating, 60% energy reduction in insulated pipe and heat loss, and a 25% reduction in overall volume of water aging in pipes, which, as I said, could be more if the hot water fixtures were co-located. Another approach would be to use a central just to boost the water from the incoming to the single temp, and then use the main mixing valves for that single temp system. And then you could use more centrally located small point of use heaters or group fixtures together to use much smaller heaters located near those hot water use fixtures. I want to briefly touch on codes that drive and some of the things that are codes that drive some of the decisions that we'll make in their current language. The Uniform Plumbing Code just has hot and cold water required, and it doesn't actually say where that hot water has to be used or what the temperature is. What that code's main goal is to prevent scalding. The International Plumbing Code is a little bit more clear. It says in non-residential occupancies, hot water, tempered water shall be supplied for bathing and washing purposes. I'm not sure if this code has caught up to the last several years of studies about hot water not being necessary for or effective for hand washing. And California OSHPD, for example, has us providing 105 to 120 degrees for clinical. They don't specify what that clinical means, but it's widely interpreted as hand washing, and that puts us right into this temperature growth range for waterborne pathogens. FGI, Facility Guidelines Institute, actually makes an allowance for using between 70 and 80 Fahrenheit water for a single pipe for showers and other end-use devices requiring heated water, for hand washing. Showers and other end-use devices would require regular hot water. So in summation, the idea here would be to wash hands somewhere in this temperature range. Temperature ranges are always arguable, and it depends on the quality of water that you have and what's in it. And supply hand wash fixtures with a single pipe system, reduce the growth of Legionella and other waterborne pathogens, reduce energy use for heating water, you eliminate hot water dead legs where bacteria grows, you reduce water age, and you reduce first cost and ongoing costs. That's it. Thank you.
Thank you, Brian. Okay, so I think we'll now address a few of the questions from the audience. If you have a question, please submit it using the Q&A tool on the toolbar. And then we'll have all the speakers, if you want to unmute your camera or whatever, we can have the speakers come up and answer. All right. So there were a few questions coming in for Troy. I think he's answered a couple, but I still think it might be helpful for the others to hear kind of the answers. There was one question that said, for Troy, is the quick purge auto trickle approach limited to showers, or can it be applied to other domestic hot water end uses?
Yeah,
and, yeah, go ahead.
I think it's a really good question. Probably the other really applicable spot in the home would be for kitchen faucet use. That's probably the other big point of use where people do definitely want hot water and they have to wait for it to get there. So an approach there could work. We would need to look at how to productize it and do those types of things, and also code, because there's flow rates that have to happen. But that's probably the other big application that I can think of off the top of my head.
Great, thanks. And then I think another question you might have answered, but I think is also a good question, is was the wait time testing completed in single-family homes or multifamily buildings? And is the long wait time scenario more prevalent in either of those building types?
Yeah, so the data that we have, the times were taken out of single-family homes. We've got data from Pennsylvania and also from Northern California. I really don't have a good answer on if there's a difference in multifamily or single family. It really depends on how that multifamily building is connected. I think that you'll see, based off of typical energy savings calcs, there'd be a slight difference between multifamily. Multifamily actually might even be a little bit more wasteful than single family, but they're pretty close to each other on all the data that I've seen without looking at our specific data.
Thanks. And then I'll move on to a couple questions because we have quite a few for Brian, and then come back to some that were for Troy as well. There's one question for Brian. You mentioned that hand washing occurs much higher in healthcare than bathing. What you are talking about is also 100% relevant to office buildings, which have almost all hand washing and typically no bathing. So I guess more of a comment. I think there's another comment from Tim as well about a key item you missed is that you reduce or eliminate the complex plumbing components more likely to grow Legionella, the point of use mixing valve. This design would be hugely beneficial in healthcare, offices, and schools, all of which have little bathing use. I don't know if you want to expand on any of that.
No, that's a great point. I was rushing along. I did try to touch on the idea of eliminating some of the real estate for waterborne pathogens, but Tim really does hit on a good point there, because if you compare the difference between a two-pipe system with a mixing valve and a sensor faucet and all the little parts that go into that at every single fixture, it really adds up. Eliminating that is a great benefit, I think.
And then we have a question about how the code bodies are responding to this idea.
Well, I've been talking about this for 7 years, I think now, and it really runs the gamut. My biggest interface is with the California OSHPD, and I've been talking to them about it for a long time, and I just recently, again, received a lot of interest in it. They don't feel like they're ready to approve it, but I was able to forward them a letter from the CDC saying that they think that 75 is a perfectly safe temperature for hand washing. Some of the more, I've received a little bit more pushback from on smaller projects in smaller jurisdictions where the code people have been less willing to step out and really examine something that they're not comfortable with. I've also had a lot of interface with infection control people. One of the biggest concerns is whether or not 75 is warm enough to not discourage washing hands for the full protocol. But I think it depends on your age, really, and your age and your body type, what you feel is comfortable. So it's really what I'm trying to do is open up this idea and get people thinking about it. And I'm not trying to tell anybody that they need to do it right away, but especially infection control professionals, if they feel like it's going to negatively impact. But I want to get the seed planted because we need to start reducing our carbon footprint now.
Thank you. Yeah, I think we did have a comment / question about how in winter, cold water can be very cold, and wouldn't you need to warm it up a little bit in order to make it comfortable for people?
Yeah, if you look at I was rushing, but if you look at the design examples, in both cases, if you have a colder incoming temperature, I would recommend that you boost it up to closer to the building's ambient temperature, and then the building will just keep it there. So there are a lot of different opportunities for creativity in how you boost that up, because you may be able to use wastewater heat recovery or using some HVAC waste heat to get that smaller boost. But yes, you should. I wouldn't recommend water below 65 probably, just because I have a temperature gun. I compare temperatures in buildings all the time, and that starts to feel uncomfortable, especially if you're having to wash for 20 seconds.
Yeah, thank you. I think we got a question for Bobbin too, so I'll move on to that and then come back maybe to Brian. So Bob, how would you characterize your domestic hot water usage? The number of people and how water conscious you are, maybe you can talk about that. And then how would you characterize your system size of the solar collector and the storage?
This is for a single-family home with a current occupants of 2, and we feed it up into a 100-gallon passive tank, and from there it feeds into a. I would say we're very conscious of water usage because we run a solar-powered pump to produce our water, so we try to minimize the amount of water that we use wherever we can. So we have very efficient appliances and such. And we're able to determine, when I first put the system in, I was able to see the flow, measure the temperature flows from the solar collectors to the tank, and then from the tank, or from the solar collectors down to the freeze protection system. And that's how I was able to determine that the system was performing as I thought it was. So, did that answer the question?
I think so. Okay. We have, I think we can move back to actually Troy has another question. I think he's in the process of answering him, but Troy, do you know that this product would have a huge impact on Legionella risk reduction? That first purge of hot water is the water that has the highest risk of Legionella. By bypassing the aerosol generator showerhead, you dramatically reduce aerosol risk.
Yeah, it's that's a really interesting point. It's not actually something that we had considered, but thinking it through, I think that makes a lot of sense, especially as the showerhead flow rates are getting lower and lower. Manufacturers are starting to do things of inject air, and you're getting more aerosolization, I'm sure, as the flows are decreasing. So it's a really interesting point, and probably an interesting opportunity for healthcare situations.
Great, and I think you had one other question that you might have answered already, but what savings have you seen in the programs that use evolved technologies?
So there's been a bunch of field research that's been done on the technology, the version of the shower start technology that we have before this new one. So let me just segment the technologies out. There's a technology called shower start that basically saves the behavioral waste. And then what we talked about today was this new twist on that technology, which is Shower Start Express, that has the really fast purge of the structural waste. So for the Shower Start technology, it's been out for, gosh, probably 10 years now. And there's been a number of field studies that have been done. Essentially, we see that technology in single-family home type of applications based on field studies is saving around a minute's worth of hot water from going down the drain for every shower. You can take that minute and then you can multiply it times whatever flow rate that shower head might happen to be. But the data that we see is around a minute on the high end. On the lower end, it's probably closer to 40 seconds. So it's somewhere between 40 and 60 seconds, depending on a particular application, on average of what you're going to save for behavioral waste running down the drain. We would anticipate that the Shower Start Express, because of the very fast velocity of the hot water arriving and basically the fast velocity of the cold water being purged, we would expect to see savings increase on Shower Start Express technology by around 50 to 100%.
Thank you. Okay, so I think these last few questions are for Brian, at least the ones we have in right now. So for Brian, are you saying that we would be allowed to design this way in California today, or do we need the codes to catch up first?
We actually have a building for a major healthcare provider, a clinic here in the Bay Area that is just been built with single temp for the hand washing fixtures. So it's really jurisdiction to jurisdiction. I was just trying to answer that question. That question's a really big one. I have had pushback from some jurisdictions that are a little bit more conservative, and they haven't really parsed out the fact that the UPC is really aimed at preventing scald. It's not trying to set a low end temperature at this point. That's not that clear. The IPC is a little bit more clear, saying you have to have that hot water for hand washing. But we have done it, and it's really jurisdiction to jurisdiction. It's right. I've been talking to jurisdictions about this for a while, just trying to soften the field for the concept. But we do have one.
Okay. Good to know. And then outside of bacteria, would having no hot water change different types of soaps coming onto the market for specific oils or dust, dirt, etc.?
I think that's an interesting and good point. Much like the soaps that started to be developed after we started, using gray water systems. I think that if you use especially cold water with certain soaps, it might slow the amount of time that it takes to remove the dirt from your hands, maybe. But you don't want to remove the oil. That's part of the dermatological health of your skin, but. It's an interesting subject, and I don't know the answer, really.
Okay. We have one other question for you. For public lavatory sinks at 0.5 gallons per minute, especially seldom used sinks in clinical settings, why not use high-performance point-of-use electric tankless?
That's a great question. There is not a great reason not to do that. The problem my range of experience in healthcare is that, as I said, like that small clinic that was only 60,000 square feet had over 100 sinks in it. OSHPD has been requiring redundant water heating for they actually went so far as to say if I had a point of use water heater, I would have to have two of them to have to provide the required redundancy. Although I'm chipping away at that, because I think that the point of redundancy was that you would not have if you had a failure of your water heater, you would have another water heater to back it up. But in the case of using a high efficiency point of use heater, that's a whole different picture. If that heater breaks, you just replace it within the hour. They haven't quite caught up to the logic behind the requirement for redundancy. I think point of use, if you have the electricity for it, is great. The other problem for kinds of projects I work on are that we have to provide emergency power, usually through the form of emergency generators. And we still have to provide as if all those were turned on at the same time. So that's a lot of infrastructure and electricity. So there's many fronts that could change to allow use of point of use in order. I mean, the best idea is to heat water only where and when you need it, right? Eliminate all that piping and real estate and mixing valves and all that stuff. But it's a struggle still at this point.
Thanks. Okay, I'm going to bounce to Troy now. Troy, does the higher flow rate on the Purge create any user concerns? Is there too much flow?
We haven't introduced the technology to the general public yet. It's about basically in June it will get launched. We haven't seen any issues at all in all of the beta testing we've done. Essentially, one thing you're not seeing in this presentation is the port now has the express port where you purge the structural waste out of. It now has a flow director on it, so you can direct the flow where you want it to go. And essentially, in a standalone shower, you want to direct it towards an interior wall. And basically, the flow immediately hits an interior wall and falls down the wall to the drain. Or in a tub shower combo, you can direct it right to the inside wall, interior wall of a tub. So you really don't get any splashing or mess or anything with the with that high volume of water being purged out, because we're able to use basically think of it as that vertical surface on the tub or a wall to tame and calm the water, so it's not splashing all over in the shower or a tub shower combo.
Okay, great. And then we have one more question for you, Troy. Do you have any information about the energy savings from the Evolve Shower Start Express?
Yeah, I would have to go back and refer to it. I don't want to just quote, but we've got papers that can show you, and there's also some papers that have been written by implementers and utilities. So I can make that available. If somebody just gets in touch with me, my contact information was in the presentation. We can get you field studies and that type of thing that will show energy savings, because it's going to depend on a number of things, right? But basically, you're either going to save gas or you're going to save electricity.
Yeah, thanks. Okay, I think we have time for one more question. So I think, Brian, we have an unanswered one here. Is there a concern that lower temperature for hand washing will encourage shorter hand washes? It seems during the start of the pandemic, we all learned that we already weren't washing our hands long enough.
Yeah, that's a good concern. I think that there needs to be behavioral change, though, in how we're using water for hand washing, especially if we're water is not the important part about hand washing, because I've been going to a lot of hospitals for field visits and I've gotten so many lessons on how to properly wash my hands. It's more about the lathering process. So we need a behavioral change where you turn the water on to have that water help spread your soap, turn the water off, and then spend your 15 to 20 seconds doing the lathering process and hitting all the surfaces, and then rinse again. I think we need behavioral change in order to make some of these things work.
Makes sense. Well, thank you again to all of our speakers for their presentations and to the attendees for participating in today's webcast. I think we might have had a couple questions slip by, so if you want to continue exploring these topics, please follow us to the Zoom chat room, and there should be a link at the bottom of your screen. So yeah, thank you so much to all the presenters, and yeah, have a great rest of the conference to all of our attendees.